Before we start, I would like to say a few words about the examples I use. As you know, I normally use processor board as an example, and your project may be different, but you can always apply the steps which we are going to speak about also on your boards. So if they are, for example, more simple, you can just skip through some of the points which we will be speaking about. But there is a lot of people who sign up for the lessons because they would like to know more about, for example, memory layout. That's one of the reasons why I speak a lot about the memory layout. And it's also useful for everyone because it's actually the kind of next step in hardware design job. You move from the breakout boards to the microcontroller boards, and then from the microcontroller boards to the processor boards, and then you need this kind of information. So I hope this is what you would like to hear, and let's speak about a little bit about what we learned last week, just to remember, and then go ahead with all the new things. Do you still remember how we start the layout? We start with memory, yes, and be specific. We start with fan-outs in the memory area under the processor or FPGA. So we place there all the capacitors and resistors which will be here. We place there all the fan-outs, all the vias which should be there. Then we place the fan-outs, the power fan-outs in the memory area, or if you use slot, in the slot area. And then we just connect the memory. That's the first part. What do you think? What is the next step? The next step is to finish the area under the processor or FPGA. We already have there some preliminary placement, but once we start putting their vias, we need to move and shift the components around. And what do you think, where we start? Do we start in this corner? Or where do you normally start? What do you think? What is the best way to start? Is it the corner? I normally start in the middle because then I can go with the components, from the middle to the edges. And the second reason why I start in the middle is because there are usually power supplies and I have to place their decoupling capacitors, and the highest important components when doing the placement are the decoupling capacitors because they need to be very close to the pin. So this is what I do first. And all the related components like these beads or ferrites or 0-ohm resistors, they need to be close. Okay? Once all the decoupling capacitors are on the place, I then do the second most important components, which are these kind of components. Some kind of reference, precise resistors or capacitors, which are normally placed just between pin and ground, but they require very often short connection and maybe wider or low impedance connection. So these are the second highest important components. Then I move to the more standard components like series resistors, which normally should be placed close to the output. For example, close to the clock, you need to place this kind of series resistor. Then it's similar for interfaces like PCI Express. These capacitors need to be placed close to the transmitter. And clocks, the crystals should be placed close to the pins. Normally, if it's possible, I try to place the crystal or oscillator on the same layer, on the same side where the processor is located. If not possible, I place it on the bottom. But the connection should be again as short as possible. Here are also some kind of components which needs to be placed very close to the pins. These termination resistors on VGA. Read the design guide and see the recommendations. Place the components which should be close to the processor or FPGA. Place them now at this stage. And then there are these kind of components which normally it's not required to place them close to the processor or FPGA. These are bootstrap resistors or pull-ups, pull-downs. But for example, very often the bootstrap resistors, in this case they go away, yeah. But many times they don't go away. They just are connected to a pin and one pull-up, one pull-down. So it's very good to place it close because I can use only very short track, and if I place it somewhere far away, I can use then the space for layout, for routing, the space which I use to connect these pins. So if I place them very close, because it's very simple connection, I can save space for some other more important things. That's the reason why I try to place all these bootstraps and pull-ups, pull-downs when they should be here. I try to place them there. Be careful, because some pull-ups or pull-downs, if they are used as termination, they may need to place on the other side of the track. So again, always read the design guide. Okay, so we have the memory, we have the processor, and what is the next step? And think about your project, because this VoIPAC one is very simple. So what do you do in the next step in your project? What I normally do, I have a look if there is no other really difficult BGA. Normally there is, because there is usually chipset, and that's the second chip what I do after the processor, and I use exactly same technique. So if you have also some other, you can have, for example, processor and FPGA, you can do the fan out for the second very difficult BGA chip. After that, next step is buses. I start with big buses, PCI, ISA. They have a lot of tracks, very difficult to do the layout if it's not done on the beginning. So why to do it on the beginning? What do you think? Because there is a lot of space. Yes. Once you start with some simple tracks and then you limit your layout, it will not be possible to do the connections for very wide buses. So that's the reason why to start with the wide bus. You have plenty of space. But be careful, before you start doing the layout for the bus, we need to do something else. What it is? We need to be sure we have all the vias, all the fan outs which will be in the way of this big bus connection, we need to be sure they are all in the place. For example, in this VoIPAC layout, let's use this as an example. Here are the biggest buses. So what would you do? Which one would you start, and what would you do as first? The fan outs. Yeah, this is very specific example because here is this connector. That's probably the thing what I would fan out between first components, and then I would do fan out in this area. So just we can repeat what we already learned. What are the fan outs? First are the coupling capacitors, then the important resistors and capacitors, reference voltages and all these things. Then series termination, other kind of terminations, clock, crystal, oscillator, and pull ups and pull down. You don't have to connect them with processor or something. Just do all the short tracks and place there all the vias, because once there are all the vias, you can see how much space you have for layout, and once you done the layout, you don't have to do it again. If there are no the vias and you do the layout, what may very easily happen is you place there the via and you need to redraw the track. So place the vias first. And in this specific case, which of these buses would you start as the first one? Would you start with this area which is really busy and looks like there will be problems, or would you start with this one which looks like it is a very simple one? Because I would start with this one. Why? Do you know why? What is the reason why I would start with this one? Because I can go to the edge of the PCB and see how much space left here. Yeah, I show you here. Can you see? I go to the edge and I actually can see how much space I have here, because I will need it. I will need this space. You can see I used it. If I start with this one, what may very easily happen is I do layout for this one, I do layout for this one, and then I find out I can't fit there this because there is no space and I need to do it again. Yeah, so think ahead and plan. And a lot of time I start from the edge. Now you have it, you spotted it. I don't do layout based on pin-to-pin connections. I do layout based on buses, based on groups, based on interfaces. So when I do layout, I do layout for whole PCI bus, for whole ISA bus, for whole display. Yeah. Why? Because it's good practice to have all the signals in the bus, in the group which belongs together, routed same way, same topology. And it's very important for high-speed design. For high-speed design, yeah, remember this. Many people ask about high-speed design. This is the example what I mean, the topology. Here I selected command memory group. This is the group which should have same parameters. see, they are all routed on the top layer. Then all the signals from this group go on the layer 3. All the signals from this group are on the layer 8. Can you see? There is no track from the processor to this group on layer 8 because they need to be routed by same way, use same topology. Go to layer 1, layer 3, layer 8 with all the signals from the group. One example why this is important: many people ask me how do I include via length in length matching. I don't because if you use same topology for every signal, you don't have to, because all the signals, they have exactly same length in the via. If you don't do it this way, there may be a lot of problems, especially when you change the stack up thickness and it starts changing. Yeah, if you have 1 millimeter from top to bottom, and then when you produce PCB which is 1.5, so from the top to bottom is 1.5 millimeter, that's different. Length in the vias is different between the stack ups. And as I said, this is good practice. Use same topology for same buses, same signals in same bus or same group. It's recommended in a lot of design guides, including Intel or AMD. It's very important for high speed design. I use the length in via as an example why to do or why to use same topology for same bus, same group, but that's not everything. For high-speed design, it's very important all the tracks have exactly same properties. If you put some of the signals on one layer, some of the signals on different layers, and do them different way, the properties of this environment may be different. For example, if you do layout and you put tracks on top or bottom layer, there is completely different environment. Like in the middle of the PCB, is completely different how the signal flies on the top and bottom layer, and in the middle of PCB it's different in the speed and all the other things which you don't need to know. Only you need to know is use same topology for buses and same groups. You don't have this kind of problems. 2 tips. At this stage of the layout, don't worry about perfect tracks. Just draw the tracks somehow, you know. It's okay if there are some loops or if they don't look nice. You will be moving them and redrawing them many times. So just connect it. The goal is connect all the pins some kind of good and proper way. How exactly the track looks right now is not important. Important is you do all the buses similar way. Yeah, you don't connect this pin like here and same pin from the via like this way. Yeah, that's what I was speaking about. You don't want to do it this way. Do them similar way. The second tip is always use wider track for power supplies and power rails, because you know, the default width of our track is 0.1 in this case. In your case it may be something bigger, depends on your PCB manufacturer. So the power tracks always make it wider, because on the end of the design, when we will be changing impedance, we will be changing all the tracks which have the default value, in our case 0.1 millimeter. We will be changing all these tracks to 50 ohm impedance, or to the required impedance. Usually it's 50 ohms. And you don't want to change the power tracks, because usually the change is to keep it 0.1 or make it even smaller. You don't want to have power tracks like 0.075 millimeter. Yeah, that's not good. They should be as wide as possible. So these are two good tips which you can use during your layout. Also, don't worry about small violations at this stage. You know, the kind of violation when you have a via, you have a track, they are very close to each other, they are green, that's okay. There is very high chance you will be moving the track anyway, you will be moving the via anyway, so we will be fixing all these things on the end. Don't try to fix it now, it's kind of wasting of time. What you need to be careful is about the big violations when you have a lot of tracks and you have via just in the middle of all these lot of tracks. You need to be sure there is enough space to go around the via, otherwise it may be very difficult to fix later, because to make space for 3-4 tracks go around the via may require moving a lot of existing design, a lot of existing layout. That's exactly the reason why I always say place the vias first, because you save a lot of time and you do the layout much faster. You don't have to do something multiple times when you have already done it. Before we move to the next mystery point, we are going to have a break, and yes, bonus time. Today I'm going to show you how big difference is in the layout between different memory chips, and you will see connection stays same, schematic same or very similar, but you will see how big difference it is in the layout. That's the point why it's always very important to read design guides. Cadence Allegro works a little bit different than Altium Designer. Difference is you select always command first. So we are going to assign colors to nets. So I will select only net, and I would like to use this green color. Now I would like to see layer 1, okay, and select only the data 0 line. Okay, it's this one. We can see it goes to series termination resistor, so we would like to see where it continues. So I just click here, and we can see it go somewhere here, because we would like to see different layer here. Yeah, on this layer it goes to the pin. So this is pretty standard data line pin to pin connection. That's as we already know it. What may be interesting, have a look how address line is connected. So I will unhighlight this net, and I use the highlight command again, and I find A8, and I would like to see where it goes. It starts in this pin. This is the address line, yeah. Then it goes to termination resistor. From the termination resistor, it goes into middle of the module, in middle of the module it splits, so it's T-branch topology. We already know this topology. It splits, it goes here and here, and there in the middle, see, in the middle, yeah, in the middle, it splits again, goes here and here, and on the top, see, on the top it connects to the memory chip. Yeah, same on the other side. So this is classic example of the branch topology. What is different on DDR3 memory? Do you know? What do you think? What could be different? I'll show you. I opened a DDR3 reference design. Just file, open this second module. And we are going to have a look how the layout is done here. So first, data line. What we are going to do now? Select command, check if we are highlighting nets, select color, and select some layers. Now I find the data line net and highlight it. It's here. Okay, and see where it continues. There is actually no difference between DDR2 and DDR3 memory in data line connection. As you can see, it goes from the pin termination resistor and to the memory. So that's pin-to-pin connection. What is different is the connection of this address line. It's not only address line, it's whole group commands, controls, and all this, but I will demonstrate it on the address line. So have a look. I will unhighlight this, highlight, and let's find A8. Okay. It looks like it is same. It's not. Can you see difference? It goes from the pin here it change layers. It goes on the edge of the memory, and then it connects to the first memory chip. It continues and it connects to second memory chip. See, it's not T-branch topology, it's called flyby topology. It continues, it connects to the next memory chip, to the next memory chip, and to the termination. So it's completely different. But in schematic, it is connection of A8 signal to all four memory chips. Connection is almost same in schematic between DDR2 and DDR3, between this T-branch topology and flyby topology. But as you can see in layout, it is completely different. It works completely different way. So be very careful, read the design guide. Why to read design guides? Because I was doing one one DDR3 design, which specifically said use T-branch topology. So be very careful. Now you know what's the difference between DDR2, DDR3 layout, and we can go back to our hard work. Once we are done with wide bus layout, we can move to the differential pairs. This is the next point. Why differential pairs? They are usually high-speed signals running on high frequencies, and they are very specific for layout because they are routed in pairs, two tracks together. So we need to be sure we have enough space to route always two tracks together. Sometimes you may have two wires very close to each other and there is no space for two tracks. That's the reason. I will demonstrate it on Voipack old design. So I will open lesson 8 Voipack version 1 issue 1, and I will use Ethernet as an example. This is the Ethernet. First, what we need to do is tell Altium Designer these are differential pairs, this is positive net, this is negative net. If we use _p, that's what tells Altium this is the positive net. _n tells Altium it's negative net. And we still need to tell Altium it's a differential pair, and it's done with this directive differential pair. Before I import these changes to the PCB, I'll show you how it looks in the PCB if there are no differential pairs specified. I go to PCB, differential pairs editor, oops, all differential pairs. See, there are no differential pairs. Now I'm going to update the PCB with the changes which I've done. So design update. I don't want to add these rows. Here you can see it will add differential pairs. Now, see, here is differential pair from Rx and Rxp, plus minus differential pair. Yeah, so Altium now recognize the differential pairs. What is the reason why we want Altium recognize differential pairs? Because they are quite important signals and there are rules how they should be routed. Voipack, they don't use rules, so this is how differential signal is routed on the Voipack board, and there is a better way to do it. Differential signals should look like this. Yeah. Same width, same gap all the time. Even the bias needs to be close to each other. And on the end, for some very high speed signals, even the signals between themselves need to be length matched. This is the length matching between the signals. This is not differential pair routing. How we do it properly? We set up rules. The rule which you can set up at this stage, because we don't know exactly what our differential pair geometry is going to be, we will know all the information once we set up PCB stackup. At this stage, we just need to be sure we have enough space for the signals. So I just specify basic differential pair, and I use minimum clearance I use as this gap, and minimum track I will use the track width. So the minimum clearance is 0.15, minimum track is 0.15, so I will specify the gap 0.15. Sometimes the gap is maybe better to make it wider, this default gap, because some differential impedances in total may be a little bit wider than minimum track plus minimum clearance plus minimum track. Some differential pair impedances have much wider track or much wider gap. So if you have enough space, specify this default gap, maybe double of your clearance. But from my experience, if I specify it as double, I have a lot of trouble to do the layout. So I normally start with the gap just as the minimum clearance. Okay, we can now do the proper differential pair routing. I will delete these polygons because they will make a lot of violations during this example, and I don't want to confuse you. Now we have now space for the layout. I delete this, and I delete also this via. I move this via here. I move this track. Oops. Why? Because I would like to have same length here and same length here. So my via, I would like to place my via somewhere here and somewhere here. Yeah, or maybe nicer. So I need to go with this drag, I need to go around. As you can see, now I only use the standard one track routing. But from here, I can use the special one. It's this button. Yeah, I need to be pretty sure I have 0.15. Nice, no? Much better. I'm pretty sure you got the point. Activity for this week for you will be to practice differential pair layout. Have a look on the Voipax schematic and find what differential pair interfaces they have there, and go to the PCB, try to have a look how they did it and do it better. When you finish with your differential pairs, you know, PCI Express, SATA, clocks, Ethernet, USB, there is a lot. When you finish this, have a look on your PCB and try to locate the unconnected interfaces and buses with longest connection, like this one. See, it goes through whole board almost. This is the kind of bus which needs to be connected now, because we would like to use same topology for all the signals in the bus, and to do so we need space. At this moment, at this stage of the layout, there is still quite a lot of free space, so that's the reason why it is the right time to do the longest interfaces. When you connect this one, the longest one, locate the second longest one and connect. And if all the interfaces which left unconnected are similar length, or the length is not important anymore, have a look on the number of pins and logically connect the one with highest number of pins. When you connect it, move to the interface with second highest number of pins. That's logical. I'm pretty sure you do it this way anyway. So we have all the interfaces connected basically, and in the next step we are going to connect local connections, local circuit. These are usually small circuits. Many times they can be routed on one layer or just minimum number of layers. These are power supplies. These are for example, connection between connector and RS-232 transceiver. That's a very good example. It's very local. There is direct connection between these two components. So the local connections are the kind of connections where most of the tracks is in the small area and only minimum of the tracks goes out or in to this area. One tip when you are doing these local connections, because the PCB is almost done at this stage, the tip is pick up a corner and work systematically. Usually I start from bottom right corner and go through whole PCB systematically. So go to the middle or go to the edge. Why systematically? Because you can clearly see how much you have done and how much needs to be done. It's very important, especially if the layout takes several weeks. It's important for you to see the progress. It helps your mind, it's much better than if you work here and there, and after a few weeks of work the PCB still look unfinished and you can predict how much work is still there, how much work needs to be done. That's the reason why work systematically and separate actually what has been done and what needs to be done. It's very helpful. And also you need to have some kind of process, because how would you be picking up randomly where you are going to work? When you have clear definition, you exactly know, when I finish this I will do this, when I finish this I will do this. That's also very helpful. When you finish all these local connections, and one more point, local connections, these are also the connections which we were speaking about few weeks ago. These are the analog connections, for example. They are very local. They are not mixed together with digital signals. So these are also local connections. Houston, hello, Houston, we got a problem. Hello, hello. I'm just kidding. I had to wake you up, and I will use this short break to show you where you can download the reference design of the DDR3 and DDR2 memory module, which I was using during the bonus time. So you can download the layouts here on JEDEC website. This is the DDR2 memory, this is the DDR3 memory, and if you would like to view these files, you will need to also download the Allegro free physical viewer. Let's go back to the other things. And when all the local connections are connected, everything what left are just very simple nets, usually one wire nets or something very simple like LEDs or power management, you know, which switch on, switch off, power supply. These signals are not usually important. You can use as many layers as you need, as many wires as you need. You can fit these kind of tracks anywhere where is space in your layout. So finish these simple tracks on the end, almost on the end, because on the end we are going to connect what left. Do you know what left? What is still not connected? Power supplies. This time I don't mean the components between power supply. I mean the power supplies in whole board. You know, you have power supply 3.3 volt here, but there is a lot of components on your board which is powered from this local 3.3 volt power supply, which has to be connected. So you need to design a plane to connect these power supply vias, these power supply pins. But at this stage I don't use planes. I preliminary always connect these power vias just with tracks, because it's much more simple to edit tracks than power planes. And sometimes I need to see how I'm going to create the power planes, how they will be exactly designed. Why? I give you example. Imagine you have 3.3 volt via here, and you have all the other 3.3 volt vias like here. Yeah? Now you have option. You can connect this 3.3 volt via this way, or you can connect this 3.3 volt via this way. What is the right connection? What do you think? It depends what is in this area. So if in this area there are nets or wires which are connected to power supply, which is located here on the bottom, then the best way to connect this 3.3 volt wire is this way, because then you can connect this power supply this way. Yeah, you understand where I'm going. And it's much more simple to, when you use just tracks, to kind of design these kind of polygons or give you idea how your future polygons will look. Also, designing the polygons, that should not be a problem at this stage, because when you were doing placement, you were already thinking about how the power distribution will be done. If you are not sure if your power distribution is designed properly, the placement is designed properly, you can do these preliminary power connections on the beginning, just after the placement is done. Or sometimes I do it if the board is very difficult, if there is a lot of power supplies. Sometimes I do this kind of preliminary power distribution just after I place the components. But most of the time, when everything is correctly planned, you can just do it on the end and it fits perfectly. Also, it depends how many layers you can use for power planes. So if you are very limited with power layers, consider some kind of basic connection to do on the beginning of the layout, just after the placement. But only very rough connections. You don't have to connect every power pin. You got it, yeah? You understand what I'm speaking about. And that's it. It's almost done. I don't draw the polygons, the power planes now. I only connect the tracks. Everything what left is clear the violations. Again, I work systematically. Initially, I start with the most difficult areas. And once all the most difficult areas were cleaned, then I pick a corner and go from the corner and clear all the small violations. So pick up on the beginning, pick up the most difficult violations, and if all of the other violations what left are very similar, pick a corner and work systematically. Once this is done, all the pins are connected and there are no violations. And this is end of phase 1 of PCB layout. Now is the time to start thinking about impedances and PCB stack-up. What are the impedances? What do you need to know about impedances? There is only one very important thing to remember about impedances. We need to match them. Match, it means transmitter impedance, the track, the layout, the track impedance, and the receiver impedance, they need to be matched. You remember the calculator from the first lesson, do you? There were two results. One was very bad when the impedance was not matched. And the second result was much better when the impedance was matched. When we match the impedance, we can get the best quality signal as we can. And there are some other benefits of matching the impedance. If you are interested about this problematic, you can find a lot of material on the internet, you can study it. But the key point is to match the impedance. That's our goal. How do we know what kind of impedance we have to match? We use design guide. Read the design guide of your chip manufacturer. They will specify it. As an example, I will use this design guide, which gives us examples of basic interfaces. And here you can actually read some basic rules during the layout, so you can learn from this. That's exactly the way how I learned to do a lot of designs. I read all these rules and then I just use them in the next and next and next design. Here are the impedances. For PCI Express, our goal is to do the layout, routed the tracks, the differential tracks, with differential pair impedance 100 ohms. That's our goal. That's what we should do. USB, we should use 90 ohm differential pair impedance for USB. Yeah, because then you will get the best quality of the signal and all the other benefits which are connected with the meeting the impedance. What is important, many people meet this differential pair impedance, but they completely forgot about this single-ended impedance. Single-ended impedance is only on one track. Differential is between two tracks. And actually, when you have differential, signals, there are actually tracks. Yeah, this is one track, this is another track. Even these tracks need to have this single-ended impedance, 55 ohms. This 55, this together 100 ohms. Many times what happens, people try to meet these 100 ohms, but use too thin or too wide track, which is not then 55 ohms. It will be completely different impedance, so they don't meet this single-ended impedance. Be careful about this. Some other basic impedances, Ethernet, read datasheet, many times it's 100 ohms. Here they specify 95 ohms. SATA 100 ohms. LVDS 100 ohms. Yeah, so you got it. These are differential pairs. Also for single-ended buses, like here is example PCI bus, they specify the impedance 55 ohms, IDE 55 ohms, and actually I use these 55 ohms or 50 ohms as a basic impedance for all signal tracks in my designs. This is important. That's exactly the reason why I use same track width for all the signals. I use that 0.1 millimeter, the minimum track width, and on the end, when I know all the information about my PCB, all the information about these impedances, I know how I can achieve 55 ohms. On the end of the design, I change all the 0.1 millimeter tracks, signal tracks, to the width of the track, which is 55 ohms. How do I know what is the right width? What is the width of the track which measure the 55 ohms? How do I know this? You can calculate it. There are a lot of calculators. A lot of people use this one. I use this one too. It is actually a very good one. But for simple demonstration, I will use this calculator from PCB calculator impedance. But I need to say before I show you, I demonstrate you how the impedance depends on what parameters and what are important. I need to tell I almost never calculate the impedance by myself. I just send the impedances, the request for the impedances to my PCB manufacturer, and they suggest all the geometry based on the technology they use. They also suggest the PCB stack up which they can manufacture. What very often happened before, when I was doing different way, when I always calculated the impedance, I designed my stack up. What happened before, the PCB manufacturer, they said they don't have this material, they can't design this PCB stack up, and they had to calculate it anyway. So that's the reason why by default I don't calculate the impedances, but we are going to see how it can be done. So what is impedance? Impedance is just a number which you can calculate based on some basic parameters. For example, for differential pair, the parameters are width of the track, gap between the tracks, and the height of the electricum between the tracks and reference planes. Reference planes are normally ground, and sometimes it may be power plane. Important is it needs to be full plane, not interrupted, not pieces of planes. It needs to be solid plane. That's the reference plane for for the tracks. And then you just press calculate. See, for the width 0.15 and space 0.15, the differential impedance is 100 ohms, single-ended 60 ohms. If I change track width, differential impedance is 90 ohms and single-ended 55 ohms. Pretty simple, no? Looks pretty simple. For single-ended, exactly same. There is different calculation for impedance on top and bottom layers, and different calculator for impedances in middle of the PCB. See, here is also top and bottom layer for differential. This one is in the middle. It's not difficult, but it may be time consuming sometimes, because when you design your PCB stack up, you need to find the right ratio between your minimum tracks, between what manufacturer can achieve and manufacture, what your maximum thickness of PCB can be, what are your required dielectric thicknesses. All this needs to be considered, and sometimes stack up can be designed very quickly. Many times happen it needs couple of days, couple of weeks. Sometimes communicate with PCB manufacturer to achieve what you want. From the Altium Designer, you already know how PCB stack up look and where we defined it. Right click, options, layer stack manager. So it's like copper, dielectricum, yeah, a lot of stuff. This is how it looks in real PCB. This is actually one of my PCBs, cut it and measured. Here are the tracks, the copper, here is the dielectricum. And when you are designing your own stack up, you need to use some materials which the manufacturer, they normally buy them. They are standard materials with standard thickness. And here are some examples of the materials which you can use when you are designing your stack up. Core, that's the kind of material with dielectricum in middle and copper on both sides. Prep rack, that's just dielectricum. And copper foil, you know, it goes on the top and bottom. This is everything what you need to know to build your own stack up. Speak to your PCB manufacturer if they have this material, if they can produce this kind of stack up. There are sometimes some limits. For example, the limit what is the minimum prep reg, or different kind of combinations cannot be used. That's the reason why you always need to speak to your PCB manufacturer if you are designing it by yourself. If you ask your PCB supplier to design the stack up for you, you will need to send them something like this: layer description, required impedances, describe the vias which you are going to use, and the thickness of the PCB. And they will send you back something like this. This is one of the documents which I received from one of my PCB manufacturers. Here is the stack up which they suggest with all the dimensions and parameters. And here are all the impedances which I requested with all the track geometry which I need to follow to achieve the impedances. So for example, if I want to have 90 ohms differential tracks on my PCB which uses this stack up, I need to use 95 micrometers width tracks on the top and bottom layer, and the gap will be 155. micrometers, and in the middle of the PCB I need to use 75 micrometers with tracks with 205 micrometer gap between the tracks, and then I will have impedance 90 ohms. Very important thing, some impedance calculators use the total thickness of the copper. Some calculators use the material thickness in one place and the plated thickness somewhere else. You need to fill both numbers to get this total thickness of the copper. Plated, during this process, during the plating of the PCB, the thickness of the layer will grow. Yeah, so it will not be actually the thickness of the material, but during the plating it grows, so the total thickness is much bigger. And as I said, some calculators use these numbers in two different places: in place where you specify the material, in place where you specify the thickness of the plating. If you forget to set this number, you will get completely different results and completely different numbers during the impedance calculation, so don't forget. And that's it. We have done the phase 1 of the PCB layout. Everything is connected, all the errors are cleaned, and next week we will be speaking about how to improve the layout, how to check the layout. Activities for this week: have a look on the Voipac baseboard and go through the differential pairs in their design and improve them, make them better. Second thing is, try to define your own PCB stack-up if you have your own project, or you can use this PCB stack-up which I have here. Select a impedance calculator, fit there all these numbers and check it. See what the results, what kind of results you will get, and play with the numbers. Try to make the track wider, gap wider or smaller. See how the impedance change. Just play with it. That's everything for this week. Thank you very much for watching and see you next week. Bye bye.